Alright, welcome everybody to the channel. Today is our 10th lesson. Yay! We reached 10 lessons so far, that's good. As I said last time, this video is going to be different from the previous ones because I want to show you not just some questions and how we answer them, but the actual properties of power numbers and how we show those properties. I know that I'm a little bit late with this video, but my schedule has been very busy these days. But I'll try to make another video until the end of this week. Okay, so this week hopefully we'll have 2 lessons instead of 1. Now, let's just start with the video. First, what is a power number? So a power number is a number of the type a, and we have this exponent here n, where a is different from 0 and n belongs to the set of integers. So n is a whole number. It can be positive, it can be negative, it can be 0, but we're not going to deal at this point with fractional exponents. So we don't want to have, for example, 2 to the power of, let's say, 0.5. We are going to discuss those numbers much later. Okay, they're much more difficult to calculate. But now let's just give an example. So a power number would be, for instance, 2 to the power of 3. Okay, we read 2 to the power of 3. Okay, and by definition this simply means 2 to the power of 3, we just multiply 2 by itself 3 times. Okay, so this will be 2 times 2 times 2, which is 8. All right, so if we want to make this a little bit more precise with the appropriate terminology, a to the power of n, this is a power number. A is called the base, n is called the exponent. So the base is simply which number are we multiplying by itself, and the exponent means how many times are we multiplying that number by itself. As in the example I gave you, 2 to the power of 3, 2 is the base, 3 is the exponent. So this means that we're multiplying 2 by itself, and the exponent indicates how many times we're doing that. We're multiplying it 3 times by itself. Okay, so 2 to the a to the power of n means a times a times a times a, etc., times a total of n times. Okay, this is the definition of a power number, as we are going to consider it as 6th graders. All right, now if this is clear, let's consider the main properties of power numbers. So the first, let's just write it as main properties. And the first, we're going to consider this: a to the power of n times a to the power of m is a to the power of n plus m. All right, the same restrictions apply in all the properties. So a has to be different from 0, and n and m have to be integer numbers. All right, so for instance, if I have 3 to the power of 2 times 3 to the power of 3, this will give me 3 to the power of 5. Okay, I just add the exponents. 2 plus 3 equals 5. And you can make a check, right? Let's make a check. 3 to the power of 2, sorry. 3 to the power of 2 is 3 times 3, which is 9, all right? 3 to the power of 3 is 3 times 3 times 3, which is 27. And then 9 times 27 is 243, okay? And if I multiply 3 times 3 times 3 times 3 times 3, I will see that the result will be again 243, all right? So if I want to prove this in the general case, so a to the power of n times a to the power of m, this is by the definition, I use definition, a times a times a times a, this is a total of n times. And then I continue multiplying it, times a times a times a, this is n m times. And obviously this is going to be equal to a times a times a times a total of n plus m times, which is a to the power of n plus m, all right? So as I said here, look, if you have 3 to the power of 2, this is 3 times 3, and then if I continue multiplying it by 3 to the power of 3, which is 3 times 3 times 3, I have 3 multiplied by itself, a total of 5 times, okay? So this is 3 to the power of 5, okay? B. Now, in the same manner as I have multiplication, I can have division. A to the power of m divided by a to the power of m equals a to the power of n minus m, okay? If I have a division of power numbers with the same base, I just subtract the exponents. So for instance, 3 to the power of 6 divided by 3 to the power of 2 is 3 to the power of 4. 6 minus 2 is 4. And I can make a check. So 3 to the power of 6, let's write it in terms of a fraction. This is 3 times 3 times 3 times 3 times 3 times 3 over 3 times 3. And now, by the properties of fractions, I can simply reduce this fraction. I can divide the numerator and the denominator by 9, so these 3's will cancel. And I'm only left with 3 multiplied by itself 4 times, 3 to the power of 4, which is 81. You can make a check. You can divide 3 to the power of 6 is 729. 3 to the power of 2 is 9. 729 divided by 9 will be 81, okay? You can make this check also. If I want to prove it in the general case, I have a to the power of n over a to the power of m. I proceed in the exact same way as in the example. A times a times a times a, this is n times, over a times a times a times a, this is m times. And if I start reducing this one with this one, this one with this one, etc., I get a to the power of n minus m times, okay? That's it. Let's go to the third one. If I have a times b to the power of n in brackets, I open the brackets by applying the exponent to each of the factors of the base. So this will be a to the power of n times b to the power of n. Okay. For instance, if I have 6 to the power of 3, this is the same as 2 times 3 to the power of 3, which is the same as 2 to the power of 3 times 3 to the power of 3. And you can check it. So if I make a check, 6 to the power of 3, this is 6 times 6 times 6, this is 216. 2 to the power of 3 is 8, 3 to the power of 3 is 27, and then I have 8 times 27 should equal to 216, all right? If I want to prove it in the general case, a times b to the power of n by definition is a times b times a times b times a times b da 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 a times b a total of n times, and then I simply rearrange the terms. So this is a times a times a times a times a n times, and then I start multiplying by the b factors, b times b times b da 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 b n times, which is obviously the same as a to the power of n times b to the power of n. Okay. By the same token, if I have a over b to the power of n, again I have a to the power of n over b to the power of n. For example, 2/3 to the power of 3, this is 2 to the power of 3 over 3 to the power of 3, which is 8 over 27, because by definition 2/3 to the power of 3 means that I need to multiply the base by itself 3 times. So this is 2/3 times 2/3 times 2/3, and then you know how to multiply fractions. You multiply numerator by numerator, denominator by denominator. This is 8 over 27. Okay, and if I want to write a proof in the general case, I proceed by the exact same way as in the example. So proof a over b to the power of n is going to be a over b times a over b times da 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 a over b, a total of n times, which is I multiply a by itself n times in the numerator, which will give me a to the power of n. I multiply b by itself n times in the denominator, which will give me b to the power of n. Okay. All right, so a, b, c, d. Then another very important is a power to some other power. For instance, not for instance, but the property is a to the power of n to the power of m. This will give me a to the power of m times n. I just multiply here the two powers. For example, 2 to the power of 2 to the power of 3, this will be 2 to the power of 2 times 3, which is 2 to the power of 6. Okay, make a check. So 2 to the power of 2 is 4, so this is going to be the same as 4 to the power of 3, 4 times 4 times 4, which is 64. And if I see that if I multiply 2 by 2 by 2 by 2 by 2 6 times, I'll get to 64. All right. If I want to write a proof of that, a to the power of n to the power of m, by definition, now this whole thing here is my new base, and this is going to be my exponent. So by definition, I need to multiply the base by itself m times. So this is a to the power of n times a to the power of n times da 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 a to the power of n a total of m times. And now I need to apply my first property, which tells me that when I multiply bases with power numbers with equal base, I need to add the exponent. So this will be a to the power of n plus n plus n plus da 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 plus n, a total of m times, which will give me a to the power of m times n. Okay. A, B, C, D, E, F. Okay. So far, we have considered what happens with exponents that are positive integers. Okay. But now, what happens if the exponent is either 0 or a negative number? So the next property tells us that a to the power of 0 equals 1. That means any number which is different from 0, if I raise it to the 0 power, that will give me 1. For example, 3 to the power of 0 is 1, 1/2 to the power of 0 is 1, etc. Okay? Minus 3 to the power of 0 is 1, and so on and so forth. How do I show that? Proof. I simply apply the division rule, the second rule that I've stated earlier. So if I have a to the power of n over a to the power of n, now you know that I can cancel this because they are the same and the result will be 1. But in terms of my division rule for power numbers with equal bases, I know that I have to subtract the exponents. So this will be a to the power of n minus n, which is a to the power of 0. Okay. If I want to substitute for concrete numbers, I have, let's say, 3 to the power of 3 over 3 to the power of 3. This is obviously 27 over 27, which is 1. But if I want to write it as a subtraction of exponents, this is 3 to the power of 3 minus 3, which is 3 to the power of 0. Okay. This is why 3 to the power of 0 will be 1, because it's like dividing the same number, 3 to the power of 3 by 3 to the power of 3, 27 by 27, okay? Then the next one is A, B, C, D, E, F, G, G, is it G? Okay. The next one is a to the power of minus 1 will give me 1 over a, the reciprocal of a. And again, this follows by the same division method. So if I have a over a to the power of 2, I cancel, this is a over a times a, I cancel this and I get 1 over a. But in terms of my division rule, this will be a to the power of 1 minus 2, which is a to the power of minus 1. Alright? Any number which is just the number itself is to the power of 1. Means this number is multiplied by itself only one time. For instance, let's say 3 to the power of minus 1 is 1/3. Because this is the same as having like 3 over 9. 3 over 9, 1/3. What else? Okay. I think this is evident why that is the case. A to the power of minus 1 is like a to the power of 0 minus 1, which is like a to the power of 0 over a to the power of 1, which is 1 over a. Okay, and yeah, you can write the proof in this manner if you want. Then the more general, the more A, B, C, D, E, F, G, H, the more general property here is a to the power of minus n is 1 over a to the power of n, which proceeds in the same manner. This is a to the power of 0 minus n, which is a to the power of 0 over a to the power of n, which is 1 over a to the power of n. So for instance, if I have 3 to the power of minus 2, this is 1 over 3 to the power of 2, which is 1 over 9. Okay. And then even more general than this, so A, B, C, D, E, F, G, H, K. let's write it K. The more general even than this is like a over b to the power of minus n is b over a to the power of n. How do I show that? Well, I showed by the previous rule. This is my base. So if I have to make the reciprocal of the base, so proof a over b to the power of minus n is going to be 1 over a over b to the power of n. So the previous rule, this rule here, h, says that the base has to go into the denominator, and then you change the sign of the exponent from minus to plus. So if my base now is the whole fraction a over b, this a over b goes into the exponent, and I change the sign of this base goes into the denominator, and I change the sign of the exponent from minus to plus. This is the exact application of the previous rule, this one here. So now if I want to apply the rule that says that if I have a fraction in the base, I can remove the brackets and both the numerator and the denominator will be affected by the exponent. So I can write it as 1 over a to the power of n b to the power of n, right? And now if I have 1 divided by this fraction here, 1 divided by a to the power of n b to the power of n, you know that to remove the division I can write it as a multiplication with the reciprocal fraction. So this is going to be the same as 1 times b to the power of n a to the power of n will be b to the power of n over a to the power of n, which is b over a, the whole thing to the power of n. Okay, and this is how I show this property. So for instance, if I have 3 halves to the power of minus 4, this is the same as 2/3 to the power of 4. This is a very useful property here. And the last thing that I want to show, let's call it J, is what happens if we have a negative number as our base. So what happens if I have, for example, minus 2 to the power of 4. Now let's apply our definition. This is minus 2 times minus 2 times minus 2 times minus 2, 4 times multiplied by itself. Now minus 2 times minus 2 is plus 4, because minus times minus gives a plus. And then I have another minus 2 times minus 2, which is another 4, which is plus 16, all right? But what happens if I have minus 2 to the power of 3? This will be minus 2 times minus 2 times minus 2, only 3 times. And now these 2 will give me 4, but then this 4 will be multiplied by a negative number, by minus 2. So 4 times minus 2, this is going to be now minus 8. Okay? So in general, if I have a positive number to some exponent, doesn't matter whether this exponent is positive or negative, I'll get a positive result. So a to the power of n is going to be positive if a is positive for any n belongs to the set of integers, but a to the power of n is going to be positive if a is negative and n is even. Okay, so in the previous example I had minus 2 to the power of 4. Minus 2 to the power of 4 gives plus 16 because the n, the exponent, is an even number, because I have an even number of minuses multiplying each other, and every two minuses, when we multiply them, they'll give a plus. So finally the result is positive. But so a to the power of n will be positive, and a to the power of n will be negative if a is negative and n is odd. Okay, minus 2 to the power of 3 will be minus 8. Minus 2 to the power of 5 will be minus 32, and so on and so forth. If I have a negative base and an odd exponent, I'll get a negative result. Okay, and those are all the properties that we need to know. Wow, we covered that in like 25 minutes. So that's good. Let me give you some application of these problems from a collection of problems that I really like. So we are going to take a few problems from this collection of problems. This is Kosta Kularov 1985 collection of problems. I'll tell you what the problem is asking us to do. It will be just either calculate the expression or simplify the expression, but in my view this is really one of the best, if not the best, collection of problems from high school and pre-high school algebra. So let's go to exercise 97. This is on page 26 in the book. So the question is, can we compare the expressions a and b? Can we say that a is bigger than b or b is bigger than a? Okay. In other words, is it possible if we can calculate the value of these expressions, where m is an integer number? So let's try to solve this. Let me just copy it here. First, let's try to present everything as having base equal to 7. Okay, so 1/7 is the same as 7 to the power of minus 1. All right, you remember the previous property, 7 to the power of minus 1 is 1/7. And now this whole thing is to the power of m minus 3. Now 49 is the same as 7 to the power of 2, and I copy 7 to the power of m minus 4. All right, now I apply here the property which says a to the power of n to the power of m equals a to the power of n times n. So I multiply these two exponents here, and I get 5 times 7. When I multiply by minus 1, I just change the signs of the terms. So I get 3 minus m times 7 to the power of 2 times 7 to the power of m minus 4. And now I have 7 as my base here, 7 and 7. So when I multiply, this is the very first property, when I multiply power numbers with equal bases, I just add the exponents. So this is 5 to the power of 7, 5 times 7 to the power of 3 minus m plus 2 plus m minus 4. Minus m plus m will cancel. This is 5 times 7. 3 plus 2 is 5 minus 4 is just 1, so this is 35. Okay, and this is my answer for A. Let's go to the next one. So this is going to be, I add the exponents here, 1 plus 2 plus 3 plus 4, which is what? 10, 3 to the power of 10, divide by 3 to the power of 7, and I get 3 to the power of 10 minus 7, which is 3 to the power of 3, which is 27. So obviously A is going to be greater than B, because A is 35 and B is 27. Alright, yeah, we got the results here. Okay, now let's solve some of these problems here. Let's go for 99. Show this expression as a power number with base 4. So you can see the answer is 4 to the power of 3n minus 1. So we need this to be 4 to some power number. Again, n belongs to the integers. Let's write this down. So I'm multiplying this number by 4. So I get 4 to the power of 4n over 4 to the power of 1 times 4 to the power of n, right? And by applying the first property, I add the exponents in the denominator, so I get 4 to the power of 4n over 4 to the power of n plus 1. And now I'm going to apply the second property, which tells me that if I have a division of powers with the same base, I just subtract the exponents. So I get 4 to the power of 4n minus n plus 1, which is the exponent in the denominator, and I get 4 to the power of 4n minus n minus 1. You know, this minus changes the signs of all terms in the brackets. So finally this is 4 to the power of 3n minus 1, right? 4n minus 1, n is 3n, and that's my answer here. Let's go to the next one. Same condition, show this expression presented as 2 to some power 2n plus 1, 2 to the power of n plus 2 to the power of n plus 2 to the power of n plus 2 to the power of n. Same procedure, n plus 1. This is 4 times 2 to the power of n, 2n plus 1. Now 4 is 2 to the power of 2. Add the exponents in the denominator. I get 2 plus n. And now subtract the exponents. Plus n minus n cancel. 1 minus 2 is minus 1, which is 1/2, and that's my answer. Let's go with the next one. Same, presented as 5 to some power. So I have 5 to the power of n. Now 0.5, let me write it, you know, more in details. 0.2 is the same as 1/5, okay? So I'm going to write it in this manner: 1/5 n minus 1 over 125 is the same as 5 to the power of 3, 2 minus 2n. And now 0.04 is the same as 1 over 25, okay? 1 over 25 to the power of minus 2, okay? Now 5 to the power of n. 1/5 is 5 to the power of minus 1, n minus 1. Here I can multiply, so 5 to the power of 3 times 2 is 6, 3 times minus 2n is minus 6n, times 1 over 25 is 5 to the power of minus 2 to the power of minus 2. Okay. 5 to the power of minus 2 is the same as 1 over 5 to the power of 2, which is 1 over 25. Now remove these brackets here. So 5 to the power of n times 5 to the power of 1 minus n. 5, 6 minus 6n times 5 to the power of 4. Minus 2 times minus 2 is plus 4. Now again add these exponents because I'm multiplying in the numerator and in the denominator. So I get 5n plus 1 minus n plus 1 minus n. These cancel. 5, 6 minus 6n plus 4. Okay. This will be the same as 5 to the power of 1 over, I add 6 and 4, 10, so 5 to the power of 10 minus 6n. Again, subtract the exponents, 5 to the power of 1 minus 10 minus 6n, 5, 1 minus 10 plus 6n, which is 5 to the power of 6n minus 9, and that's the answer. Okay. 102. Show this expression as 2 to some power. Actually, because we're not given an answer here, try to do it yourself. Try to present this as 2 to some power. Okay. If you need, pause the video here and try it. So 4 is 2 to the power of 2 to the power of m times 0.25 is 1/4, 3 minus m. 0.125 is 1/8 minus 2 over 2, 3m minus 5. So far so good. Remove the brackets here, multiply 2 times n, we get 2 to the power of 2m. 1/4 is the same as 1 over 2 to the power of 2, which is 2 to the power of minus 2. 2 to the power of minus 2 to the power of 3 minus m. 1/8 is the same as 1 over 2 to the power of 3, which is 2 to the power of minus 3. 2 to the power of minus 3 to the power of minus 2 over 2 to the power of 3m minus 5. So I get 2m times, I multiply minus 2 times 3 minus 6, minus 2 times minus m is 2m, so 2m minus 6, minus 2 times minus 3 is plus 6. And then I just add the exponents in the numerator, so 2m plus 2m minus 6 plus 6, this will cancel, 3m minus 5, so 4m over 3m minus 5, subtract the exponents, 4m minus 3m minus 5, this is 4m minus 3m plus 5, which is 2m plus 5. Okay. And finally, let's try to compare this a and b. Which one is bigger, which one is smaller? So let me copy a first. So what do we have here? Minus 4 times 1/2 to the power of 2y minus 7 times 12 times 12, 2 to the power of minus 1, 10 minus 2y. Okay, I can actually multiply minus 4 and 12, I get minus 48 times, now this is, I actually didn't need to present this 1/2 as 2 to the power of minus 1 because I have another 1/2. So actually let me keep this, let me just keep this as 1/2 instead of 2 to the power of minus 1. Let me keep it as 1/2 like this. And now I'm going to multiply this one and this one. So I get 1/2 to the power of, I simply add the exponents because I have the same base, which is 1/2. So I get 2y minus 7 plus 10 minus 2y. 2y minus 2y will cancel. So this is minus 48 times 1/2 to the power of 3. 10 minus 7 is 3. 1/2 to the power of 3. 1/2 to the power of 3 is 1/8. Like this, 1/2 times 1/2 times 1/2 is 1/8. So minus 48 times 1 over 8. I reduce here, get minus 6. So a equals minus 6. So let me actually write it as a fraction. It will be easier. So this is 27 times 1/3 5x minus 1 over 1/2 times 1/3 5x minus 3. Now I can divide them separately, so I can divide 27 by 1/2, right? And 27 divided by 1/2 is like 27 times 2, which is 54. And then I can divide 1/3 to the power of 5x minus 1 by 1/3 to the power of 5x minus 3. And this will give me 1/3 to the power of 5x minus 1 minus bracket 5x minus 3. Okay, so this is 54 times 1/3. I remove the brackets, I get 5x minus 1 minus 5x plus 3. Change the signs. 5x and minus 5x will cancel, so this is 54 times 1/3 to the power of 2. 3 minus 1 is 2, so this is 54 times 1/9. 1/3 times 1/3 is 1/9, so I reduce here. 54 divided by 9 is plus 6. Okay, so b is plus 6, a is minus 6, so b is going to be greater than a. Okay, thank you so much for watching. If you have any questions, let me know in the comments below. And as I said, I'll try to make another video by the end of this week, and it's going to be about linear equations or equations with one unknown of the first degree. If you enjoy the content, like and subscribe, and I'll see you in the next one. Bye for now.